Let's now go on to one of the most important sections in this particular chapter is dealing with the classification of sets. How are sets classified based on the specific properties? And we begin with the empty set, the null set, or the void set. And as the wording itself indicates, it means that the set is empty or the set contains no elements. Now, it's denoted by phi or just by drawing braces without any element. Now, the point here is that if you put phi and draw brackets around it, then it indicates a single element, which simply means that we are not dealing with an empty set. So you mustn't do it like that. Let us look at two examples. Set A, which X is an element of capital R, that's a set of real numbers, and X squared is equal to minus Z, that is the square ending up as a negative integer. As I have already mentioned in the previous video, such a thing is not possible because we always get positive integers unless we are dealing with cases like minus 2 into 2 or something like that, which can be solved only under complex numbers, and we'll be discussing those portions in a very detailed manner in the chapter of dealing with complex numbers. And so the answer is that such a thing is not possible, or choosing an element which ends up as a negative integer is not possible in that particular case, which means that there's no element in that particular set. Another set B, which is an element of natural numbers, and the element ought to be between 5 and 6. Now we know that natural numbers deals with countable numbers. That's 1, 2, 3, 4, which simply means that there's no number between 5 and 6, which simply which indicates very straightforward that we are dealing with a set which doesn't have any elements in it. Let's go to the second kind. It's called a singleton set. Again, the word itself indicates what we are dealing with here, a set having only one element. Suppose we are dealing with a set D, which again consists of elements. The set the X, the arbitrary element X is an element of natural numbers, and X squared is equal to 16. Now it simply means that X ought to be a rule of 16, that is 4, which simply means that we are dealing with only one element, that is 4. Another set P, which is again X is an element of N, and set of natural numbers, and X comes between 8 and 10, and as in the previous case where we discussed about empty sets, here we can see that there can only be one countable natural number between 8 and 10, and that of course is 9. So set P has one element, and that is 9. Now let's look at the case of a finite set. What do you mean by a finite set? Means that the elements are countable, and of course the elements have to be distinct, which means that the character is very clear. There's no confusion in the kind of character. So the finite set means that the set contains countable. That means when you look at the countable natural numbers, we can denote a number which indicates the total number of elements inside it. So if countable natural numbers are indicated by A1, A2, A3 up to AM, then the cardinal number means the cardinal number of a set indicates the number of distinct elements of that particular set. So cardinal number is indicated by n of something of a set. So here if I denote a set as A, then cardinal number of A in this particular example is M. That's AM. As M is the number at which that particular series is ending. So the cardinal number of that set in A is M. Now, interestingly, because of its particular definition, the OID set or the MD set and the Singleton set are also naturally finite sets. Suppose we are looking at the case of cubes, that is the set C, which consists of x cube. That element is a cube. It's and also it belongs to natural numbers, and it comes between 9 and 90. Naturally, we have to select those numbers which are cubes and which come between 9 and 90. Of course, it's a finite set. And when we deal with finite sets, naturally the first thing we ought to look into is the infinite set. And infinite set simply means that you cannot list it by natural numbers. So it is infinite. Now, the property of infinity in mathematics actually doesn't indicate a particular number. It simply means that if you denote a number, it simply means that you can let's go to that number plus 1. So it is a concept more than a number. Now, infinite set means that you can't denote a particular number to list, or you can't denote a particular number in the natural number system to list the number of elements coming in the set. That's the meaning of it. And you have an interesting we have two interesting examples coming up from coordinate geometry. In a Cartesian plane, theoretically, the set of all points is actually infinite. That's also the case of all lines coming in that plane. Now, in real numbers, we know that a huge number, in fact, infinite real numbers can be considered between two countable numbers and between two numbers. So if I denote a set D, which is so X is an element of real numbers, and it's coming between 0 and 1. As we are dealing with the real numbers, now real numbers play a very important role in mathematics, and actually we'll be dealing with this particular number set, a huge number, again and again. So in this particular case, we are dealing with an infinite set. Thank you.